Welcome back to the AI Frontiers podcast, where we delve into the cutting edge research shaping the world of artificial intelligence. Today, we're diving into a fascinating paper that tackles a critical challenge in training massive deep learning models: pipeline parallelism. Joining me today are lead researcher's name, a leading expert in distributed deep learning, and field expert's name, a renowned AI researcher with a keen eye for the bigger picture.
Thanks for having me.
It's great to be here. So, could you introduce us to the paper and its central contribution?
Certainly. This paper, titled Zero Bubble Pipeline Parallelism, tackles the problem of pipeline bubbles, which are essentially wasted time and resources during the training process. Imagine you're training a massive language model on a cluster of GPUs. You divide the model into stages, like a conveyor belt where each stage processes a different part of the data. The challenge is that the stages have to work in sync, and sometimes a stage might have to wait for another stage to finish its work. These waits are called bubbles, and they significantly decrease the efficiency of training.
That's a great analogy. So, the paper's key innovation is to address these bubbles, right?
Exactly. Traditionally, the backward computation, which updates the model's weights, has been treated as a single unit. But we realize that this backward computation can be split into two parts, one for computing gradients with respect to the input, and another for computing gradients with respect to the parameters. By doing this, we can schedule these parts more flexibly, essentially filling the bubbles with useful computations. This is a crucial step towards achieving zero-bubble pipeline parallelism.
That's very interesting. Could you elaborate on how this split impacts the scheduling of the computations?
Sure. In our paper, we propose several scheduling strategies. First, we developed handcrafted schedules, which we call ZBH1 and ZBH2. These schedules carefully place the parameter gradient computations to fill the bubbles, allowing for more efficient use of the GPUs. For example, ZBH2 achieves zero bubbles, but it requires a slightly higher memory footprint.
So, these handcrafted schedules are like carefully designed blueprints for the computation process. But how do they account for real world scenarios where execution times might vary?
That's where the automatic scheduling algorithm comes in. This algorithm takes into account the real execution times of different computations, memory constraints, and communication overhead, and it automatically generates an optimal schedule that minimizes bubbles.
It sounds like a sophisticated approach, but how does this algorithm actually find the optimal solution?
We use a combination of heuristics and integer linear programming, ILP. Heuristics provide a good initial solution, and then ILP fine-tunes it to find the best possible schedule. This way, we can achieve close to zero bubble rates while respecting memory limitations.
That's fascinating. So, Field Xname, what are your thoughts on this approach? How does this research fit into the larger landscape of deep learning training? This research is very exciting, especially as we move towards larger and more complex models. The ability to eliminate pipeline bubbles is critical for scaling up training to thousands of GPUs. It allows us to harness the full computational power of these clusters without wasting valuable time and resources. The automatic scheduling algorithm is particularly interesting as it adapts to real-world conditions, ensuring optimal performance across different setups. Could you elaborate on the implications of this research for training large language models? It's a game changer. Training large language models requires an enormous amount of computational power. With this new approach, we can train models faster and more efficiently, potentially accelerating the development of even more capable and sophisticated models. This research has the potential to push the boundaries of what's possible in natural language processing and other domains. That's certainly an exciting prospect. Could you tell us about the experimental results and how they validate this approach?
Our experiments show significant performance gains compared to the existing methods. We evaluated the performance of our methods, ZB1P and ZB2P, on a range of models from 1.5B to 28.3B parameters using up to 32 GPUs. The results are clear. ZB2P consistently outperforms 1F1B and interleaved 1F1B, often achieving up to 31% higher throughput. We also found that the automatically generated schedules have nearly zero bubble rates. This proves that our approach is effective in harnessing the full potential of pipeline parallelism.
That's a substantial improvement. So, what are the limitations of this research and where could it go from here?
One limitation is that our current work focuses primarily on transformer models. Future research could extend our approach to other types of deep learning architectures. Another limitation is that we primarily focus on pipeline parallelism, while data parallelism is an equally important aspect of distributed training. Future research could explore how to integrate these two approaches more effectively. Finally, our current post-validation strategy for bypassing synchronization has some overhead, and we're looking for ways to further optimize it.
Those are important points. What other avenues of research do you see as promising based on this work? I'm particularly interested in how these methods could be adapted for different communication topologies and network configurations. As we move towards larger clusters of GPUs, the communication overhead becomes even more critical. Exploring efficient communication strategies within the context of pipeline parallelism is essential for maximizing performance. Additionally, this work could be extended to handle more complex scenarios where models might be divided into multiple pipelines or even mixed with other types of parallelism, like tensor parallelism. The potential for further optimization and generalization is vast. Those are compelling points. So, lead researchers, to wrap things up, what are the most crucial takeaways from this paper?
This research highlights the importance of rethinking traditional approaches to pipeline parallelism and exploring more flexible scheduling strategies. By splitting the backward computation and using an automatic scheduling algorithm, we can achieve significant performance gains and push the boundaries of training massive deep learning models. It's a major step towards harnessing the full potential of distributed training for advancing the field of artificial intelligence.
That's a great summary. Any final thoughts? This paper is a prime example of how innovative thinking can lead to significant breakthroughs in deep learning. It's clear that the quest for more efficient training methods is crucial for pushing the frontiers of artificial intelligence. I'm excited to see how this research inspires further advancements in the field. That's a perfect note to end on. Thank you both, lead researcher's name and field expert's name, for this insightful discussion. Listeners, you can find the paper and open source implementation at link. If you'd like to delve deeper into this research or other exciting topics in AI, be sure to check out our previous episodes and subscribe to the AI Frontiers podcast for more in-depth discussions with leading experts in the field.